For this example, we're going to do a simple current density to current conversion so that we can get just to warm us up to the idea of using current density and relating it to quantities that we're familiar with, like current. We'll start with, we're given a cylindrical wire in this case, and so we will have a cross section that looks like this, and over here we have current density that will be given, and this is it's heading in the z direction, so we'll set the coordinate system such that it's nice and convenient. We're given that the current density is going to be some number times rho squared in the z hat direction. The current, so therefore we see the current goes this way, and the current is actually a function of rho. So as at the center, the current is 0, and then as you move away from the center, the amount of the current density goes up in a parabolic shape, right? So this is actually the amount of current that you would see as you go away from the center. And as I mentioned before, we're trying to do the conversion between the current density and the current. So the question in this example is, what is the associated current? The relationship between current density and current, so talked about current density is a density, right? Amps per meter squared. So to convert that into current, you just integrate that over the entire area, right? So I have the amount of water flow density going through as a function of location going through this cross-sectional surface. So if I wanted to know the total amount of water flowing through it, again using the water analogy, then I just add it all up, right, across the entire surface. And so what remains is mostly a review of how to set up and execute this kind of surface integral, which I think is important enough to just do one or two more times. So over here, our JS, we were given that's J naught rho squared in the z hat direction. Next, we want to define the surface ds. The normal direction is in the z direction, so the direction of ds. We use a vector that's normal to the plane to define the direction of the plane. And again, if you can go in two directions, up or down, in this case, since the current is flowing upwards, you usually use the direction of the current or the outward direction, whichever the case may be, and use that as your normal vector. So in this case, the normal vector is z. And to draw this out, if you were to draw out this cross-sectional area, you'd have to vary two variables, right? One is rho, so you would have d rho. And then the other is you want to one way to draw a circle is to change the radius from 0 to rho and then rotate it all around 2 pi, right? So you also have d phi. Again, d phi isn't a unit length, so what do we have to do to convert it to unit length? Have a rho, right? So always, whenever you write d phi, you should automatically have a rho next to it. Another way is, once you've figured out one of these elements, you can figure out the other two. In this case, we figured out that the direction normal to the surface, this unit vector, is z. Therefore, the ds, the other two dimensions, right? So if this is z, then the other two dimensions are rho and phi. So you can also use that to get to the result that you want. I forgot to mention the radius is given, so we'll just call that a. And that's basically all there is to it. We'll just set up the integral. We have our j naught, this rho, so the z dot z is going to be equal to 1, so we don't have to worry about this z anymore. The rows combine, so you end up with rho to the third, d rho d phi, where rho goes from 0 to a and phi goes from 0 to 2 pi. Now once you have this set up, I like to just do some reorganization so that you just have single variables to worry about. So the rho, we have rho cubed going from 0 to a. And then for phi, we don't really have any phi terms, so it's just d phi 0 to 2 pi. So now solving this integral by parts, for this rho, we have 1/4 rho to the fourth, evaluated at 0 and a, which is going to be equal to 1/4 a to the fourth. And this integral is simply going to be 2 pi. So plugging that in, we'll have j naught 1/4 a to the 4th, oh, this should be 4, and times 2 pi, and we are left with pi j naught a to the 4th over 2. So this is the current, and it's in the positive direction is the way that where we've defined this. And there you have it, the conversion between current density to current. So the main thing where we have to use some of the new knowledge comes into play when the current density depends on the location in some way, shape, or form. But it's just a further practice of the surface integrals that we were practicing with electric flux density, right? So we figure out what our ds is, take the dot product, clean it up, do the integral, declare victory.